Hello. Time for Unit 3, a very important, very quick, very conceptual lesson to this problem. Great job. As you guys know, acceleration due to gravity, which I'm going to write here for no reason, is a constant. It does not depend on mass. Okay, we're going to watch a cool video. Unfortunately, we're not in person. If we were, I could show you this demo, and it's really fun. I couldn't find the right string, though, so check this out. There is a large iron ball. It's solid iron, so it's really heavy. And there's two strings on the bottom, the top, very, very thin strings. If you pull on the bottom string, which string will break first? Let's watch and see. Wow, fascinating. Sage, what happens? Well, he pulled on the bottom string, and the bottom string broke first. Yeah, that makes sense. Why does that make sense? Because the ball is so heavy, it's pulling on the top string. Wait, what? Which string should break first? The top one, because it has the pull and the big heavy iron ball. Yeah, that makes sense. But in the video, the guy made the bottom string break first. Daisy, what happened? Why did the bottom string break first? Well, he was pulling on the top and not the bottom. Pulling on the top and not the bottom? This is kind of a preview for later, but if you pull the bottom string, Daisy, the bottom string pulls the ball, and then the ball pulls the top string. So that doesn't actually matter. Oh, I didn't know that. Okay, that's okay. Don't worry about it. So what the heck happened, Hazel? I don't know. Did you notice anything? Yes, I noticed a very important thing. The first time, when the bottom string broke, the student was pulling really, really fast. The second time, he pulled slowly and the top string broke. Wow, what a great observation. Very important. Let's discuss. So it was a pretty heavy iron ball. I'd say it was about 2 kilograms. That's really heavy. That's like about 4.5 pounds. Well, actually, it's equivalent to 4.5 pounds, which I'll come back to later. This ball has a lot of mass. This is the mass of the ball, 2 kilograms. It has a very high mass, but it also has a pretty high weight. The mass was 2 kilograms. The weight, it's probably like 19.62 newtons. I'm of course approximating, but it's about 19.62 newtons. What happened? What's the trick? When you pull really fast on the bottom string breaks. But when you pull slowly, you get what you expect. You expect the top string to break because the top string is already holding the big heavy ball. Here's the trick. When you pull really fast on the bottom string, the bottom string breaks. I did say the bottom string pulls the ball, pulls the top string. That's true. But if you pull so fast on the bottom string that the heavy, massive ball doesn't start moving, you can break the bottom string before you move the ball to pull the top string. The top string, this is going to sound really strange, but it doesn't even know you're pulling the bottom string. It won't get pulled until you actually move the big heavy iron ball. If you pull, just imagine an iron ball floating in space. If you pull it, does it move easily compared to like a 1 kilogram ball or like a, I don't know, like a little like a marble or something? Mass resists pulls. It's hard to pull, and that's the trick. It's so hard to pull this heavy, massive iron ball that if you pull really fast, you can break the tops, you can break the bottom string, and well, once the bottom string is broken, you're not pulling anymore, and that can all happen before the iron ball starts moving, or starts moving a lot, and before it pulls the top string to break it. This property, resistance to pulls, resistance to motion, being hard to move around, is called inertia. Inertia depends on mass. Mass is like the property of the object. It's something that has a lot of atoms, something that's very dense, something that's like made of like lead or uranium, as opposed to like hydrogen and helium, has a lot of mass. Inertia is a descriptor, it's like the property, hard to move. It's very hard to push around a big heavy truck. It's very hard to pull an solid iron ball, especially with a little thin string. That's inertia. Resistance to pulls and pushes and forces. Weight is the very first force we're learning about in physics. The symbol for weight in physics is F sub g, because weight is the force of gravity. Please never confuse mass and weight. They're not the same thing. That's why there's a line between them. Mass and weight are not the same thing, but they're definitely related. The more massive something is, the greater the Earth pulls on it. The Earth's pull on every object, markers, physics teachers, babies, everything, is called the force of gravity or weight. They're the same. These are the same thing. Mass and inertia are not the same thing. Mass is like a property of the object that you measure in kilograms. Inertia is just like tendency to not move when pulled. But weight and FG, they are exactly the same thing. And they're related. The bigger an object's mass, the bigger its weight. You could even say they're linear. If I were to, do a lab and make a graph of FG and M, I'd get a nice, perfect linear relationship. So FG is equal to mass times some constant. This constant depends on many things. On Earth, Fg is the pulling from the Earth on the object. But if you're on the moon, it would be a different value because it'd be the moon pulling on the object. If you're on Jupiter, it would be a different value because it'd be Jupiter pulling on the object. It depends on where you are, but if you're on Earth's surface, it's always the same constant. And you'll never guess what letter we use to describe it. It's a lowercase g for gravity. Again, don't call this gravity and this gravity. Call this weight or the force of gravity. Call this g gravitational field strength. I know I'm being very annoying, but if you call it gravity, I'm not going to know which one you're talking about. So this is gravitational field strength. This is Fg, force of gravity, or weight. And what is that constant? It is constant for the whole Earth. There's another constant for the moon and another constant for Jupiter. But for Earth, it's 9.81 newtons per kilogram. We just saw the most important unit of the unit. It's force. Mass is in kilograms. Forces, all forces, including weight, are in newtons. And a newton is also known as a kilogram times a meter per second squared. That's what a Newton is. A Newton is a derived unit, like meter squared or meter per second squared, but we use it so much it has a special name. It's a Newton. Do you notice anything interesting about this number, about the units? Something we've talked about before? Tell me what you notice about 9.81 newtons per kilogram. Yes, Sage. It's the same as 9.81 meter per second squared. Yeah, you're right. The units cancel out. It's exactly the same. What a strange coincidence. Fg is m times g, the same g as the acceleration due to gravity. But notice, it's not an acceleration due to gravity right now. It's a gravitational field strength. I'm going to talk a little more about that, but it's not an acceleration. Here I have a Tibetan singing bowl for no reason. The Tibetan singing bowl has a mass. It's like, I don't know, maybe like 200 grams, 0.2 kilograms, something like that. It is being pulled downward by the Earth with a force m times g. It is experiencing gravitational field of this strength. But what's the acceleration of the bowl? Is it 9.81 meters per second squared? No, it's at rest. It has zero acceleration. It does not have any acceleration due to gravity. It's not a projectile. Hopefully, it's definitely not a projectile because I'm gonna get like yelled at if I break it. But it's it does have this gravitational field strength. It does not have this acceleration. Yes, they're the same value. Moving on. So, mass and inertia are related. They're all related to weight, but they're not the same thing. And it's very hard because on Earth, they're linked, but not everything on Earth really has this exact connection. You guys ever heard of the Macy's Thanksgiving Day Parade? Probably. Here we have a nice picture. It's a Pikachu balloon. It's kind of weightless. It doesn't really have any weight. It's floating. This is not technically true, but it's good enough for our lesson today. This is a weightless balloon, a float. That's what they're called. And look at all the people. There's like 20 people holding ropes carrying this balloon down the street. Why do you need so many people if it's a weightless balloon? Couldn't I just take my 3 babies and give the 3 babies the string or the rope and say, hey babies, go walk down Fifth Avenue and pull this Pikachu and you can be the parade today because we're social distancing and we're not going to have a crazy parade like this. Is that going to work? Tell me what you think. Could 3 babies pull the entire balloon? It's weightless. Would that work? That wouldn't really work. Even though the balloon is weightless, it still has a lot of mass and a lot of inertia. There's a lot of like canvas, the ropes are heavy, there's probably like connectors, there might be some kind of internal structure. Definitely, even the air inside has mass. It doesn't really have weight. It does, but it acts like it doesn't have weight, but it has a lot of mass. It would be really hard to pull it. You couldn't like if you couldn't tie the balloon to a bicycle and ride the bicycle like 20 miles an hour down the street. It would be too hard to pull a giant balloon because of all its inertia. Yeah, so that's inertia and weight. We're gonna look at something related really soon, but that's the main idea for this whole lesson. Mass and inertia are one thing. Weight's another thing. They're not the same, but they're related by the equation I just showed you guys. It's super important. We're going to talk about something else before we finish because it's going to pay dividends later. Just trust me. If I go over this idea, it's going to save me a lot of headache later. And you guys too. It's going to save me a lot of, it's good. Don't worry. Here I have a point. I'll call it point P. point P is near Earth. It's near Earth's surface. In case you weren't curious, in case you didn't know, I'm not in space right now. I'm still on Earth. I'm going to put something at point P. Here it is. I got it. I'm going to put this nothing right here at point P. Bam, nothing. Is there gravity at point P? Answer that question now. Is there gravity at point P? All right. I know it seems weird. I put nothing at point P. So I put an object with zero mass at point P. Therefore, the weight of the force of gravity on that object is 0. If I put 0 kilograms, then of course, I'll get 0 newtons of force. So would you say there's no gravity at point P? No, that doesn't make any sense. Of course there's gravity at point P. Point P is on Earth, near Earth's surface. Let's say I put a 3 kilogram rock, which I happen to have. It's a 2 kilogram. It's a 2 kilogram rock. If I put a 2 kilogram rock, it will experience force of gravity of about 19.6 newtons. Let's say I put a 1 kilogram baby at point P. A 1 kilogram baby will have a weight of 9.8 newtons. So if I put a baby at point P, there will be gravity acting on it. If I put a rock at point P, there will be gravity acting on it. If I put nothing at point P, there's no force, there's 0 newtons force of gravity on that nothing. But we won't say that there's no gravity at point P. Hopefully that makes sense. Even though the force of gravity is 0, we still say there's gravity there. The way we describe that, we say point P is in Earth's gravitational field. If I were to draw the Earth, that's what the Earth looks like. You could, if you wanted, draw arrows all around it, showing the direction of the force of gravity. Side note, actually super important note, but side note. Gravity is a force, and therefore a vector, and therefore has direction. But for point P is near Earth's surface. Man, there's point P right there. You can't see it, it's very small. Point P is in Earth's gravity field. At point P, there is a gravity field of strength 9.81 newtons per kilogram. If you put 0 kilograms of mass at point P, it will experience 0 newtons of force. But that doesn't mean G is 0. If M is 0, Fg is 0. That makes sense. But G is not 0. You're still in Earth's gravity field. That might have been kind of irrelevant, but it's super important for a future topic. We'll see in like February. See you then. Just kidding, see you right now. Look at this video. It's pretty cool. This astronaut is gonna grab a bag of tea. It's kind of like a big Capri Sun, and there's some air in the middle. He's gonna, does he explain it? I don't remember if he saw this or not. He's gonna spin this bag. There's a big bubble in the air in the middle. Or it's actually like on top, although there's no top in space, so weird. Okay, sorry, let me start over. You know how, what's it called? When you're drinking like a soda, the air bubbles go to the top. They come out of the soda and they go to the top, they go up. But in space, they don't do that. There's no gravity, there's no up. They're gonna go all over. Be right back. Okay, what was I talking about? Physics stuff? The bag of tea. He's gonna spin the bag. If I were to spin something, things would like go off to the edges. Like if I have a alright, don't tell anyone I'm doing it. If I spin a baby, this is a terrible example. If I spin a baby, all their blood will go into their head. That was a really bad example. If I spin this little like you can't even see that. This is teaching I'm gonna cut this all out. Okay, I'm back. So we're talking about the tea on the space station. The astronaut's gonna spin the bag of tea. And let's see and what do you think is gonna happen? Well, if I take my headphones and I spin them in a circle, they get pulled to the edge of the circle, right? Yeah. So, Hazel, what's gonna happen? Well, if he spins the bag, I think that the bubbles will be pulled to the outside of the circle. So the bubbles will go all the way around the outside of the bag. Interesting idea. Let's see the video.
I have this bag of tea, and you can see it has bubbles in it, but they don't rise to the top. In fact, I'll shake them up here, and you can see the bubbles spread out throughout the tea. The bubbles don't rise to the top in the absence of gravity in this weightless environment of the space station. But if I were to rotate this, and let's see if I can rotate it and keep it in your view of the camera. Let's watch what happens. If you look really close, you'll see the air bubbles starting to coalesce in the center of the tea bag. In fact, let's see, when I bump it, they move. I'm trying to get it in your view here. There it is in your view. They make a perfect circle, unless I disturb it. Let me try that again. See the air coalesce to the center, form a circle. Due to the centripetal force applied in this, because it's turning, it's rotating, the liquid goes to the ends and the air ends up in the center of the liquid. Very interesting. As soon as I stop, you can see the liquid disperses throughout.
Well, Hazel, were you right? No. Sorry, but it's okay. Hazel thought that, oh, the bubbles are the things that will get pulled to the outside because the bubbles are the things that rise in a soda. But that's not really happening. It's all about mass. Bubbles don't really have mass compared to the tea. The tea has a lot more mass. So when you spin the bag, it's not the bubbles that get pushed to the outside. It's the tea. The tea goes to the outside, so the bubbles actually go to the inside and make a big bubble in the middle. Pretty cool video. All you really need to know is this equation. It's on the equation sheet, so could just read that. But remember, G is 9.8. It has the same value as 9.8 meter per second squared, but it's not the acceleration. It's not the acceleration of my baby, unless I were to drop my baby, which I definitely would not do. So it's not acceleration of gravity. It's gravitational field strength. Bye.